Okay, hello everyone. So in this video I'm going to be going over some photoelectric effect exam questions, IBDP Physics Higher Level, 2016 to 2018. So let's just get started. We have the usual setup for photoelectric effect question. We are told here that violet light is shining on C, our metal cathode made of cesium. And there is a current in that case, which means, of course, that the photons of the violet light, they have enough energy to knock out electrons and overcome the work function. So, but when we have, let me see, when the violet light is replaced by red light of the same intensity, then the current is zero. So we have to explain that. And of course, obviously, when we switch to red light, we have a longer wavelength, which means a smaller frequency, which means a smaller photon energy, and that photon energy is not enough to overcome the work function. So we need to write that down. So let's start by saying that photons of violet light, they have enough energy initially, and the energy of a photon is hf. Okay, first statement, I guess we get a point for that. So here we are explaining how the photons of the red light, they have less energy. And then we tie it all up. So the red photons, if we write it like that, the red photons don't have enough energy to overcome the work function of C, so the current disappears as no electrons are knocked out. Something along those lines. You can, of course, write this much better than I did right now, but these are the main points. Okay, next question is that we are looking at the current, how the current depends on the potential difference, and this is when we are using violet light. So remember, so you can see that this negative 1.15 voltage is the stopping voltage. Okay, so that's how much we need to adjust our power supply to in order to deflect all the electrons, and the current becomes zero. If we were to increase that voltage, make it less negative, then some of the electrons would make it over to the anode, and we would have a current. And of course, if we make the voltage positive, then we sort of suck all the electrons over onto A, so we get the maximum saturation current. And we are now increasing the intensity without changing its wavelength. Okay, so if we're not changing the wavelength, we're not changing the frequency, which means we're not changing the energy of the photons. So we will have the same stopping voltage. So it has to start at the same voltage. But if we have a higher intensity, it means we have more energy per unit area per unit time. And that means we get more photons, which means we get more electrons. So in the end, we get a higher current. So what we have to do here is we have to draw a line that starts at the same stopping voltage because the photon energy doesn't change. But everywhere else we get a higher current because we do get more electrons since there are more photons due to the increased intensity. So we get a higher, so this is at the high intensity. Okay. Then we have to find the work function. Okay, so for that we look up the stopping voltage. We can see that on the graph. That's sort of the magnitude of the stopping voltage. So that of course tells us the maximum kinetic energy of the released photons, because that is how much energy it takes to slow down the fastest moving electrons. So we can now use this very important relationship. Okay, this is super important to understand this one. Just the photon energy, subtract the work function, gives you the maximum possible kinetic energy. And we want to find the work function. So it's just the photon energy, which we know because we know the wavelength, minus the maximum kinetic energy. Okay. So we can sort of plug in. We know that frequency is speed over lambda, and we know the maximum energy in EV. Okay, and then what we can do, we can actually look up HC in the data booklet. If you look in the data booklet on, I think it's page 3 or something, you can see HC is given in 2 different units. And one of them is 1.24 10 to the negative 6 EV meters. Now the wavelength we have here for violet light is 400 nanometers. Okay, meters cancels out. We're going to get EV. Subtract the 1.15 EV. And if you do that, in the end, you get something like 1.95 EV. So that's the work function. Yep, good. Then the voltage is now adjusted to positive 2.5. So again, we're sort of sucking all the electrons over to the anode. And the maximum kinetic energy that they can have at the anode is therefore going to be the maximum kinetic energy that they have when they are released from the cathode. Let's call it Ke max at C. That we already know is 1.5 EV. But then now the electrons, these fast moving electrons, are then further accelerated across 2.5 volts. So let's write that down. And furthermore, accelerated across 2.5 volts, which gives us a sort of an increase, a further increase in kinetic energy. That is 2.5 EV, right? Charge of the electron times the accelerating voltage. So in total, hence, in total, the maximum kinetic energy at the anode is the sum of those two, 3.65 EV. Okay. Good. On to the next one, May 17. Got these 2 observations, and we have to explain how each supports the particle theory, but not the wave theory, right? So remember the photoelectric effect, which was something Einstein explained this phenomenon in 1905 using Max Planck's photon concept. And this is actually what gave Einstein his Nobel Prize. In, I think it was 1921, he got that. And yes, so the photoelectric effect could not be explained by classical physics, by assuming light is an electromagnetic wave. So we're back to the particle theory of light. So his explanation supported the particle theory of light. So the first observation, that below a certain frequency no electrons are emitted. So in terms of the particle theory, we explained that by saying that the photons just don't have enough energy to knock out an electron to overcome the work function. So photons don't have enough energy to knock out, in quotation marks, to knock out an electron. Although there really is sort of a collision taking place between the photon and the electron, and then all the energy of the photon is transferred to the electron. Okay, so that's sort of how we explain that using the particle theory of light. And then the wave theory can't really explain that, because if we assume light is an electromagnetic wave, then we know from waves and oscillations that the energy sort of an oscillation does not depend on the frequency, it just depends on the amplitude of the oscillation. So so it should be possible, even though we have say a low frequency, it should be possible to have a large enough amplitude to, say, knock out the electrons, but it turns out not to be the case. So let's try and write that down. So we can write that the energy of a wave doesn't depend on frequency, only amplitude. So it should be possible to knock out electrons at all frequencies in a way. There shouldn't be this threshold frequency, because we could just turn up the amplitude, increase the energy of the wave, and then it should be possible. But yeah, so it because it's not possible, then explaining the photoelectric effect, or this effect, sort of supports the particle theory of light. Second observation is that the emission is almost instantaneous, and that we sort of explain that using the particle theory by saying that the photons, of course, collide with the electrons, and they sort of almost instantly eject them from the surface, whereas a wave could take much longer, because maybe it's a low energy wave, and then the electron has to sort of absorb a certain amount of energy before it is then ejected from the surface. So one would expect it to take a bit longer. So we can write photons collide they sort of collide 1 to 1, right? One photon collides with one electron, and almost instantly ejects the electron. Okay. Maybe we should write a photon collides with an electron and almost instantly ejects the electron. A wave could take longer. take longer time since energy is being added continuously. To the electron. Sort of like, boiling water, right? That you need to add a certain amount of energy before it starts boiling. Maybe it was the same with this effect, that those electrons could be knocked out if you just shone light on it for a sufficiently long time and then they started jumping out, but that was never seen to be the case. So yeah, the photoelectric effect supports the particle theory of light. All right, let's move on. So here we have the usual energy versus frequency plot that we have to know very well. And the question here is find a value for Planck's constant. So Planck's constant is the slope here, right? Because we have to remember we're looking at a graph of this, right? So the energy versus the frequency. So h is the slope and negative phi is the y-intercept. So we just need to determine the coordinates of these 2 points. So that's an easy question. And then you have to, of course, just read off the numbers carefully and pay attention to the units on the axes, very important. So what I got here was, let's see, so it's like 4.2, so it's the rise and rise over the run, 12 minus 7.6, and then the units, right, I've got 10 to the negative 19 joules on the y-axis and 10 to the 14 hertz per second, right? On the y-axis, you plug it into your calculator, you get something like this, comes out in the right unit, and this is 6.8, 10 to the negative 34, so close enough to Planck's constant, 6.63. Okay, state what is meant by the work function. It is the minimum energy required to release an electron from the surface of the metal. Work function, yeah, let's find the y-intercept. So need to extend the line. Let's see if I can do that on my iPad here. So I think I got something like that. Looks pretty close to being -4. So y-intercept is around -4, 10 to the negative 19 joules. It has to be an EV though, so we just have to remember the conversion factor. This is -phi. Conversion factor around 1.6, 10 to the negative 19 joules per EV. We get 2.5 EV. Experiment is repeated with a metal surface of cadmium, has a greater work function. Draw the line corresponding to that. So a greater work function, of course, means we have a more negative y-intercept. So we have to draw a straight line with a more negative y-intercept. But the slope, of course, has to be the same because the slope is Planck's constant, which is a constant of nature. So there you go. Nice. Let's move on. Yellow light. Okay, calculate the wavelength. That's easy. Wavelength is hc over E. And again, I said in the data booklet, hc is given. So I just looked that up instead of wasting time calculating that. And I used the version that's expressed in joule meters because I've got the energy in joules. And I get 5.7, 10 to the negative 7 meters, which is 570 nanometers, and that sounds about right. Yellow light. Okay, then they say these electrons have almost no kinetic energy, so practically zero kinetic energy, which means that the energy of these photons is just enough to overcome the work function. The energy is basically equal to the work function. So, and why does this not contradict the law of conservation of energy? Well, because all the photon energy just went into increasing the potential energy of the electrons in the metal. So, you know, they have a lower potential energy. They're trapped in the metal. In order to kick them out, we need to increase their potential energy. So that's where the energy is going. So we just write that the energy of the photon increased the potential energy of the electron. So that it can just escape with almost 0 KE. So just to emphasize again, the HF just overcame, or was just equal to the work function. Okay. Now we increase the energy, going up to 5.2. So now we would expect photons to be emitted with kinetic energy. Let's find the maximum kinetic energy that they can have. And that's pretty straightforward, because we know that the 3.5 10 to the negative 19 joules is actually the work function. That is the information they're giving us in the previous question. So I know that if my photons now have this energy, I take away the 3.5, which is the energy required to overcome the work function, and then I have this many joules left, which is 1/2 mv squared. And then we just rearrange that. I get 2 times 1.7. And then the mass of the electron, look that up correctly, make sure everything is in the correct units. I've got joules, I've got kilograms. That works out correctly to a certain number of meters per second. Pretty fast. Okay, we continue. We have a current radiation with a greater photon energy than in B. Let's see, so B, we've got the high energy photons that create a current, but we have now, now we're gonna shine even more energetic light on. However, the intensity is the same. Describe the change in the number of photons. Okay, well, if the intensity is the same, we have the same amount of total energy. Okay, that's very important to understand. So total energy, you know, the intensity is energy per unit area per unit time. So total energy per area per time is constant. Okay, but if we have higher energy photons, then we don't get that many photons, because you have to take the total energy and divide it by the photon energy to get the number of photons. And if the photon energy has gone up, we get fewer photons for the same amount of energy. So total energy per is constant, but photon energy is larger. So we get fewer photons. The energy is divided up into fewer photons, right? So just to emphasize that. Describe the change in the number. Yeah, so that's why we get fewer photons. So total energy divided up into fewer photons with more, each with more energy, right? With more energy per photon. Okay. So if I get fewer photons, I will get fewer electrons, because the photons, they knock out, each photon knocks out one electron, which contributes to the current. But if I have fewer photons, we get fewer electrons. So each photon releases one electron. So since there are fewer photons, there will be fewer electrons, and the current decreases. Okay. Next one, now in May 18, almost done. So here we have got some hydrogen atoms in an ultraviolet UV lamp. Okay, make transitions. Okay, so basically it's sort of hydrogen creating some UV photons. So show that the energy of photons from the UV lamp is that. So, and here we need to know a little bit about atomic physics, the Bohr model. We're going from the first excited state to the ground state. So we need to remember that the energy levels of the hydrogen atom are given by this formula, which we derive also in topic 12. And since it's, and so first excited state is E1, no, sorry, is E2, and the ground state is E1, right? So that's the energy we're looking at. So delta E is E2 minus E1, where En is this. So, and then we can calculate those, of course. E2 is negative 3.4 eV minus 13.6 eV, which gives us 10.2 eV. That's roughly 10. Okay. And this is, of course, this is the energy. This is the energy HF of a photon. Okay, work function is 5.1. Calculate in joules the maximum kinetic energy. Very easy. So each photon has 10.2 eV. 5.1 eV goes to increasing the potential energy, and then we have a maximum of 5.1 eV left that can be converted to kinetic energy. And we just need it in joules. So of course 1 EV, 1.6, 10 to the negative 19 joules, and you get something like 8.2 times 10 to the 19 joules. How the variable voltage source can be used to stop all. Okay, so this is of course about the stopping voltage, the idea that, you know, if we make this plate over here negative and this positive, then we make it harder for the electrons to reach the collecting plate. They have to overcome an additional potential difference, and the voltage that just stops the current completely is called the stopping voltage. That's the minimum amount of voltage required to stop it. And so what do we do there? We write, yeah, so we just increase the voltage. So that all the so that all the kinetic energy of the electrons is converted into electric potential energy, QV. And we, of course, in order to do that, the collecting plate has to be negative to make that possible. So maybe we'll just mention that too. The collecting plate should be negative. Variable voltage can be just so that no electrons reach the, write down the minimum value of the voltage. Yeah, so the minimum voltage, you can see that because the maximum kinetic energy is 5.1 eV, the minimum voltage is 5.1 volts. That is the minimum potential difference we need. So that is the stopping voltage. Electric potential of the photoelectric surface is 0 volts, and then we adjust this so that's minus 1.2. Okay, so that's not enough to stop them all. And then we have a fun little problem where we have to draw equipotential lines, topic 10 idea, mixed into this topic 12 problem. So that's relatively easy though. You know, we have two charged metal plates. Equipotential lines are lines parallel to the plates and sort of equally spaced out. So we're increasing from 0 to 1.2 volts across a certain distance. 0.4, 0.8 is going to be 1/3 and 2/3 of the way. So you know, if you want to, you could also have identified there's halfway, and then of course I need to divide that into another 3 equal parts to get 0.2. This is going to be 0.4 volts, that one here. And then I have another one. Here we have 0.8 and 1. We had to show the 0.8 voltage one, which is this one. So maybe I'll take away the other ones like that. Straight lines. Use a ruler. Draw those lines nice and straight and make sure that they're sort of spaced out equally. An electron is emitted with that kinetic energy. Okay, so it hasn't got the maximum kinetic energy. It's one that just has that kinetic energy. And we want to find the speed it has at the collecting plate. So again, we can say, let's figure out the kinetic energy at collection. We know it's released from the surface of the metal with 2.1, but then it has to overcome a 1.2 potential difference. So that's 2.1 eV minus 1.2 eV. That's going to be 0.9 eV. That's the energy at the collecting plate, which is half mv squared. And we just need to then isolate V. 2 times 0.9, but that's in eV. Let's turn it into joules. And divide by the mass of the electron, joules, and that comes out as this. And I believe we are done. Okay, see you next time. Bye.